Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be talking about the multiple testing problem. This is what happens when you run many hypothesis tests on the same data and then report only the ones that came out significant. We're following Bess. She's an investigative journalist on a cold case she can't let go. Today she's investigating why so many quantitative strategies that look rigorous in backtests fall apart almost immediately in live trading. She's looking at a fund that has a pitch deck listing two trading signals that have p-values below 0.05. Both had been tested against 5 years of historical data, and the fund launched both strategies on the same day that they discovered them. She pulls up her case file. Everything we've covered about hypothesis testing assumes one thing, that you only ran one test on one question against one data set. You set your significance level before you look at the data, and then you run the test to get your result. The probability of a false positive under those conditions is alpha. That is the guarantee that the framework provides. But that guarantee breaks down the moment you start running multiple tests on the same data. And in practice, running multiple tests is extremely common. It happens in academic research, it happens in model building, and it happens constantly in quantitative finance, where analysts test dozens of signals on the same historical data set, looking for ones that come back significant. The problem is this. Every test you run carries its own chance of a false positive. If you run 20 tests and every single null is actually true, then the probability that at least one of them comes back significant by random chance is not 5%. It ends up being much higher than that. Here's the calculation. Each test has a 5% chance of a false positive. So each test has a 95% chance of correctly not rejecting the null. If the tests are independent, the probability that one of them produces a false positive is 0.95 multiplied by itself 20 times, which is about 0.358. So the probability that at least one of them does produce a false positive ends up being 1 minus 0.358, which is about 64%. Let's let that sit for a moment. 20 tests all run on noise, and there's a 64% chance that at least one of them comes back with a p-value below 0.05. You effectively would expect to find a significant result just because you tested so many things. The expected number of false positives from 20 tests at alpha equals 0.05 is 20 times 0.05, which is exactly 1. Back to Bess's case. The fund tested 20 signals over the 5 years of historical data. 2 came back with a p-value below 0.05 and they launched both. But finding 2 significant results out of 20 tests is not that surprising. It's basically what you predict by chance if none of the signals were real. The p-values on the individual tests each came in below the threshold, but the researchers never adjusted for the fact that they ran 20 tests. This problem goes by several names: the multiple testing problem, the multiple comparisons problem, and in financial research it's sometimes called the p-hacking or data dredging problem. This tends to happen when researchers test many signals and only keep the ones that look good and report them as if they were the only ones that they tested. There is a standard correction for this, which is called the Bonferroni correction. The idea is simple. If you want the probability of any false positive across all your tests to stay at 5%, then you need to divide your significance threshold by the number of tests. So instead of requiring p less than 0.05 on each test, you require p less than 0.05 divided by 20, which in this circumstance would be p less than 0.0025. That is a much tighter bar. In fact, neither of the fund's 2 signals actually clears it. The Bonferroni correction is conservative. It tends to produce false negatives because it sets such a strict threshold per test. In large-scale testing situations, researchers sometimes use less conservative alternatives, but the core principle holds regardless. When you test multiple hypotheses, you have to account for the number of chances you gave yourself to find something. The deeper issue in quantitative finance is what researchers sometimes call the factor zoo problem. Academic journals have published hundreds of trading signals that show up as statistically significant in backtests. Most of them decay quickly in live trading, however. A large fraction of them were almost certainly discovered through exactly this process. Enough researchers testing enough signals on enough datasets will produce a pile of false positives that look indistinguishable from any real findings, and you won't know which is which until you put real money at stake. The fund in Bess's story launched both strategies. Within 8 months, both had underperformed the benchmark by more than 2%. In her article, Bess explains this to her readers. The fund had 2 signals that cleared the bar. What they didn't report was how many signals they tested before finding these 2, and that number is what really created this story. So that's the multiple testing problem. Every test you run carries its own false positive rate. When you run many tests on the same data, those rates compound. 20 tests at alpha equals 0.05 gives you a 64% chance of at least one false positive, and you'd expect exactly one by chance alone on average. The Bonferroni correction addresses this by dividing the threshold by the number of tests. It's conservative, but it keeps the overall false positive rate controlled. And whenever you see a significant result from a large-scale search, the first question you should ask is how many other things were tested before that result was found.